so many A-level maths students overcomplicated this question in 2024, and they lost loads of marks. It's actually really simple when you realise that these modulus graphs are really just two straight lines glued together. In their report after the exams, the examiners said that part C was found to be less accessible, with few candidates scoring full marks for a correct range for K. They said that many candidates failed to realise that there was an upper limit for K, and they said that there was a reluctance amongst students to use diagrammatic reasoning, and most students resorted to complicated algebra. Many set up simultaneous equations in X and K, but didn't appear to understand what they were attempting to achieve, failing to solve for K, and therefore these lengthy attempts, I imagine, did not gain any marks. Part A, it says figure 1, which is what we've got shown here, shows a sketch of the graph with this equation. The vertex of the graph is at the point P, that's this point, as shown in the figure 1. Find the coordinates of P, so both X and Y written as coordinates in brackets with a comma in between, for 2 marks. How can we do that? Well, notice that this equation contains a modulus. Now, a modulus just takes the size of a number. Can a modulus ever be negative? No, it's just taking the size of a number. The modulus of -4 is +4, for example. Now, at the point P, notice that Y takes on its minimum value. So what would we need the modulus to be for Y to be at its minimum? Well, we'd need the modulus to be as small as possible. What is the smallest possible that this modulus can be? 0 is the smallest it can be. When would it be 0? Well, that would be when the part that's inside the brackets would be 0. The modulus of 0 is 0. So we'd need the part inside the modulus, x minus 2, to equal 0. When would that happen? Well, that would happen when x equals 2. And if x equals 2, well, this modulus part would be 0, so we'd have 3 times 0 plus 5, we'd end up with y equals 5. So you can see we've got really the 2 appears here. Notice we change the sign from -2 to +2, but we keep the sign of this +5 as it is. So if you realise that, you can just glance at the equation and really write down the answer straight away without needing to write down any of this working at all. Before we go on, I want you to understand how this modulus graph is formed really from 2 straight lines. It's actually very simple. If x is greater or equal to 2, the x value of p, so if x is somewhere here, then we're on this branch. It's a straight line, clearly. How do we find the equation of that straight line? Well, if x is greater or equal to 2, then the modulus of x minus 2, this part of the equation, would just be x minus 2. Therefore, what does this equation that we have here become? Well, I can replace this modulus part with x minus 2. And if we expand the brackets, we end up with this. And if we simplify, we end up with the equation y equals 3x minus 1. But it's important to realise that we haven't got the entire straight line, as we normally would consider when we just write this down. In fact, we only have part of the straight line. The part of the straight line where x is greater or equal to 2, the x value of p. It's not the whole straight line, just this part. So the equation of this branch on the right, the green branch, is y equals 3x minus 1. What about the equation of this orange branch on the left? Well, that would be when x is less than 2. If x is less than 2, then the modulus of x minus 2, this part of the equation, would be the negative version of x minus 2. So what would the equation become? Well, I would be replacing this modulus part with the negative version of x minus 2. If you expand the brackets, you end up with this. If you simplify, we end up with y equals minus 3x plus 11. But it's important to realise again, we don't have the entire straight line that goes on forever. No, we only have part of the straight line, the part for which x is less than 2. So the equation of this orange branch on the left would be the straight line y equals minus 3x plus 11. So that can be quite helpful. For example, we can deduce therefore that the y-intercept of this orange branch is at 11. So this point here would be the point 0, 11. What would the gradient of these lines be? Well, the gradient of the orange line would be -3, and the gradient of the green line would be +3. If we were to extend this green line onwards, you'd see that it would have a y-intercept of -1, but actually that part of the line isn't included, because remember, for the green line, it only exists for x being greater or equal to 2. Part B. Solve this equation. So we need to work out what x might equal. Well, what we've got on the right-hand side here is the V-shaped modulus graph that we've been talking about so far. But what we've got on the left-hand side is actually another straight line. The straight line with equation y equals 16 minus 4x. Or if you like, minus 4x plus 16. So it's another straight line with y-intercept at 16. And in fact, it would be a straight line that would have a steeper gradient than this part on the left. Because this gradient is -3, this one has a steeper gradient of -4. So in fact, it's going to be looking perhaps something like this. So looking at this graph, I'm expecting really there to be only one solution for x, one point of intersection. But let me prove that to you using algebra. So let's consider What happens if our x value is less than the x value of p? Remember, p had coordinates 2, 5. The x coordinate of p was 2. So if x is less than 2, well, we'd be on this orange branch over here. Remember how we found the equation for that orange branch? We said that the modulus of x minus 2 would be the negative version of x minus 2. So in this equation, we could replace the modulus part, this part here, with the negative version of x minus 2. And if you do the number crunching on all of that, you end up with y equals minus 3x plus 11. That's what we had there before. I'm just redoing that for you. But we're setting that equal to 16 minus 4x. Now, if you solve this equation that we have here, you actually end up with x equals 5. But we need to reject that solution. It can't be valid because we said that on the orange branch, x is less than 2. We don't have the full straight line. We only have the straight line up to x equals 2. So we need to reject this. We say it's not valid as 5 is not less than 2. What about the other branch? What if our x value is greater than the x value of p? What if x is greater or equal to 2? Well, in that case, the modulus of x minus 2 would just be x minus 2. So I could replace this part with x minus 2. Do the number crunching on the right-hand side, expand and simplify. We end up with, you guessed it, y equals 3x minus 1. And again, we're setting that equal to 16 minus 4x, this blue straight line here. And if you bring all the x's onto one side, all the numbers onto the other side, you end up with this. Divide by 7, we have this. Let's just see if that's valid. How many times does 7 go into 17? 2 times with 3 left over. So it's 2 3/7, which is greater or equal to 2. So this is a valid solution. So therefore, x does equal 17 over 7. And that's the only solution that we've got here. Part C. It says a line L, which has this equation, where k is a constant. Given that line L intersects this V-shaped modulus graph at 2 distinct points, find the range of values of k. So we're expecting to have some kind of inequality as our answer. It's talking about a range of values in plural. Okay, let's just remind ourselves of what we found so far. So we found out that the equation of this orange branch here was this, and it's that for values of x less than 2. And the equation of this green branch was y equals 3x minus 1. And it's this straight line for values of x greater than 2. So remember that we also deduced that the y-intercept of this branch on the left must be at 11. Let's think about the line that we've been given. I'm going to highlight it in blue here. Y equals kx plus 4. What do we know about that line? Well, it's a straight line with a y-intercept of plus 4. So let's think about where that would be on our graph in relation to the point P. The point P has y value 5. So the y-intercept of our straight line is going to be lower than that, lower than the y value of P. So maybe it might be somewhere down here, let's say, on our graph. That would be our point 4 here. Let me write it as 0, 4. What else do we know about this? Well, we know that it's a straight line, but we don't know what the gradient is. The gradient is the value of k. So this question's really asking us about what could the gradient of this straight line be? What are the possible gradients that are possible that would lead to 2 distinct points of intersection? Well, let's think about this. If I had a really super steep negative gradient, something like this, you can see that the line would only intersect this leftmost branch, and that's it. So we'd only have 1 point of intersection. If it were less negative, but still quite steep, maybe something like this, again, we still have 1 point of intersection. But if it becomes less negative still, then maybe we have no points of intersection, maybe something like this. And you can see that if it becomes less negative, if it becomes 0, again, still no points of intersection. And if it becomes slightly positive, well, again, still no points of intersection. But if it becomes sufficiently positive so it just touches at P, that's where we change from 0 solutions to just 1 solution. So that's going to be an important transition point, because any value of the gradient that's even slightly greater than that will lead to 2 distinct solutions. But there is a limit. We can't just keep increasing the value of the gradient. Eventually, the gradient of this straight line will exactly match the gradient of this straight line. And then again, it wouldn't therefore intersect this rightmost branch. It would only intersect the leftmost branch just once. So we've got a lower limit and an upper limit. Let's think about finding those. Let's think about this line here, which is kind of like our interface between 1 solution and 2 solutions. So can we work out the gradient of this line? Well, yeah, we can from these coordinates, right? We know how to work out the gradient from coordinates. We do the change in y, 5 minus 4, over the change in x, 2 minus 0. And so the minimum gradient would be, if we do the number crunching, it would be a half. What about our maximum gradient? Well, we said that that was when this line would be parallel to this line. Remember that the equation of this line we worked out earlier to be y equals 3x minus 1. What's the gradient of that line? Well, the gradient is 3. So therefore, if this is going to be parallel, it's going to have the same gradient. The maximum value of the gradient will be 3. So any gradient k that's between these 2 values would work. But notice that these are strict inequalities. We can't include those values because if they are exactly equal to a half or exactly 3, we'd actually only have one solution, not two. Do you think you'd manage to get full marks in that kind of question if it came up this summer? Let me know in the comments.